So here let us continue the acidity. So if you go for acidity of carboxylic acids, continued carboxylic acids, if you take in this, what we are noticing here is, suppose always as already I told you, acidity is directly proportional to electron withdrawing groups. Like examples we can take, that is nitro group, carboxylic group, aldehyde, all these are electron withdrawing groups. So acidity increases whenever that's because you find that it stabilizes. The reason is it stabilizes the carboxylate, stabilizes the carboxylate ion. In other words, if you are taking an electron withdrawing group, attachment is there for the carboxylate group, so you find that this is a carboxylate acid. So this ultimately it leads to the stabilization, electron withdrawing group. So what is happening here is it stabilizes both the oxygens with the negative charge. You can see a negative charge. So this is stabilizing the carboxylate ion. Stability of carboxylate ion. If it is electron donating group, acidity is inversely proportional to electron donating group. Examples you can take, that is acidity is inversely proportional to electron donating group. Examples you can take all methyl groups. You can take NH2 group is an electron donating group. You can take NH of COCH3 is also an electron donating group. So all this, they decreases the acidity. That's because if you take the electron donating group, it increases the electron density. It increases the electron density of the carboxylate ion. O minus, this comes to again electron donating group. It increases the electron density. Oxygen and oxygen, partial negative. This is destabilization of carboxylate ion. So here if you take the next case of the acidity of carboxylic acids, you can just take it like this, that is, take one question: benzene ring with the carboxylic acid, benzene ring with carboxylic acid and one methyl group, and benzene ring with carboxylic acid and one nitro group. Suppose this is A and this is B and this is C. How do you measure the acidity? Acidity, if you take, yes, this is electron withdrawing group, so it is going to deactivate the benzene nucleus and it is going to stabilize the benzene ring. So therefore the release of proton becomes easy in the case of the electron withdrawing group. This is electron donating group, so it destabilizes the stability of the benzene ring and it becomes difficult for the benzene ring or the carboxylic acid, aromatic carboxylic acid, to release the proton. And relatively, if you compare between A and B, in A the release of proton becomes easy than in the case of B. So therefore overall, if you take acidity decreasing order, if you take, then you find that here the first it is C, electron withdrawing group, next it is A, and next it is B is the acidity. This is one question where we need to understand. Second is if the vinyl group and the phenyl group, suppose for example if you are taking the vinyl group CH2 CH double bond carboxylic acid in, let me put it like this, this is vinyl carboxylic acid, and also you find that benzene ring in both these cases relatively, this is nothing but this is prop 2-ene oic acid, 1-oic acid, and this is benzoic acid. So what I am noticing here is what is happening to the acidic nature. I am just circling the carboxylic acid. What you are finding here is, one thing what we are finding is in this carbon, in the carboxylic acid, the carbon is undergoing sp2 hybridization, which is a greater electronegative carbon, is one reason. Here also the carbon is undergoing sp2 hybridization, greater electronegative carbon, and this greater electronegative carbon of the carboxylic acid can easily stabilize the vinyl group. It is going to stabilize the vinyl group. This is vinyl group. This is the vinyl group, and this is the phenyl group. So therefore here the acidity increases when vinyl group and the phenyl group C6H5 are attached directly to carboxylic acid. Increases when they are directly attached to the carboxylic acid. Take one more question here, that is, take the benzoic acid, then let this be A. Take CH2 carboxylic acid, let this be B. Then you can take CH3 carboxylic acid, OH, and this is CH3 CH2 carbon double bond oxygen of OH, let this be C, let this be D. So here what we are noticing here is, as already I told you, the carboxylic acid, this is a phenyl group, directly attached to the carboxylic acid. Here this is benzyl group. In between the benzene, mind you, the benzene ring is not directly attached to the benzene ring is not directly attached to the carboxylic acid here. Don't forget that. This is actually something like, this is a benzyl group. Benzene with CH2 is benzyl group. Here, of course, this group is an electron donating group, which contains only one carbon. Here, this is also an electron donating group, but there are two carbons here. Again, you find that there is an increase in the electron density. So obviously the electron donating group with one carbon and electron donating group with two carbons, if you decide, the electron donating group, the one which is having less number of carbons, will become more acidic than the electron donating group which contains more number of carbons, because the destabilization of the carboxylic acid is more dominant in the case of the ethyl group than in the case of methyl group. Here, because the phenyl group is directly attached to the carboxylic group, here the resonance stabilization takes place for the carboxylic acid. Here, because the benzene ring is not directly attached to the carboxylic group, the resonance stabilization of the carboxylic group does not take place because the phenyl group is not directly attached. So therefore, if you take the increasing order of acidic nature, the increasing order of acidic nature if you take, then A comes first, next comes B, next comes C, and next comes D. This is the increasing order. So here the next part of the discussion is, that is, chemical properties of carboxylic acids. In the chemical properties of carboxylic acids, reactions involving cleavage of carbon alcohol bond of the carboxylics. So in this, to name a few, let us first highlight all the important reactions which are possible in the cleavage of carbon alcohol bonds. First one is formation of anhydrides. Second is formation of esters. Third is action of PCl3, PCl5, and also SOCl2, thionyl chloride. Also action of ammonia on aliphatic carboxylates, aliphatic carboxylic acids, and aromatic carboxylic acids. These are the four important reactions where we can highlight in the reactions involving the cleavage of carbon alcohol bonds. And in the formation of anhydrides, the dehydrating agent, we need to use dehydrating agent, that is P2O5, phosphorus pentoxide you can use, or you can also use concentrated H2SO4. In the case of formation of esters, HCl or H2SO4 will act as catalyst, and in the action of PCl3, PCl5 and SOCl2 also, they are directly involved in the reaction and they give respective chlorides. Okay, final product is products. The product obtained here is, that is, in all the cases you find that acyl chlorides, you get acyl halides here, and here of course we are going to get the products obtained here are amides. So let us see what kind of reactions are possible in all these four generalizations what we made for the carbon alcohol cleavage. Let us see what kind of reactions are possible in preparing anhydrides, esters, acyl halides, and amides. So first one, if we take formation of anhydrides. In the formation of anhydrides, take two molecules of acetic acid, CH3COOH, again CH3 single bond, carbon double bond oxygen, OH. So you take P2O5 as a dehydrating agent, you heat it, one molecule of water is lost, and you get here, that is CH3 single bond, carbon double bond oxygen, again oxygen. So you get acetic anhydride. These two molecules are acetic acid molecules. One molecule of water is lost. So you can simply write this as CH3 single bond, carbon double bond, oxygen taken twice of CO. This is acetic anhydride. Similarly, if you go for the formation of ester, in the formation of ester, in the formation of ester general formula R single bond carbon double bond oxygen of R dash. This is ester. So suppose if I am taking an alcohol, if I am taking ROH alcohol plus HO of carbon double bond oxygen of R dash, reversible reaction, H plus ion, it is acting as a catalyst. So this is a carboxylic acid and this is alcohol. So from the carboxylic acid I am taking a proton, and from alcohol I am removing one OH group minus H2O. So here you are going to get the product as R dash of carbon double bond oxygen of O, single bond of O gives R. This is ester. So here take one example. If you want, you can take an example. Suppose if I am taking C2H5OH plus C2H5OH plus H of O of carbon double bond oxygen of CH2 and CH3. If I take, then same reaction, almost acidified reaction. So you get, this is going to become CH3 single bond CH2, again CH2 single bond carbon double bond oxygen O of, so remove one molecule of water minus H2O. So you get here, that is nothing but C2H5. So I can write this as ethyl 1 2 3 4 butanoate. Ethyl butanoate is the byproduct, which is the main product which we are going to get, and this is definitely an ester. The formation of ester is nothing but the characteristic feature. It gives a fruity smell, sweet fruity smell. So therefore it's a test for the alcohols and the carboxylic acids. Let's continue here. The third one, reaction with the PCl3, PCl5 and SOCl2. If you take SOCl2, so suppose if I am taking CH3 COOH plus PCl3, if I am taking PCl3, so here you are going to get CH3 single bond carbon double bond oxygen chlorine plus POCl3 plus HCl. So this is acetyl chloride. Again, go for the next case. So PCl3 is over. Now go for, this is PCl5, sorry, not PCl3, this is PCl5. PCl5 is over. Now go for PCl3, CH3 single bond carbon double bond oxygen OH plus PCl3. If you take, then you get here, that is CH3 COCl plus H3 PO3. Balance the equation. There are 3 chlorine, there is only 1 chlorine, so take 3 here and take 3 here. So this is acetyl chloride, and this is phosphorus acid, acetyl chloride and phosphorus acid. Go for the last one, SOCl2, CH3 single bond carbon double bond oxygen plus SOCl2, thionyl chloride. This is thionyl chloride, it is thionyl chloride. So here you are going to get CH3 single bond carbon double bond thionyl chloride plus SO2 plus HCl. Again you got acetyl chloride. So next part of the reaction is, that is fourth one, reaction with the ammonia. If you take in this acetic acid, when treated with ammonia, you get ammonium acetate CH3 single bond, carbon double bond oxygen, O of NH4 plus of O minus. This is ammonium acetate. Again you heat it strongly, you get minus H2O, you get CH3 single bond, carbon double bond oxygen, NH2. So this we call it as acetamide. Again, if you are taking benzoic acid, and if you treat it with ammonia, you get here ammonium benzoate, and this upon heating minus H2O, it gives you carbon double bond oxygen, NH2. This is benzamide. Similarly, if you go for the phthalic acid, if you are going for phthalic acid, say you are taking here COOH, carbon double bond oxygen, again carbon double bond oxygen, and you treat it with ammonia, 2 molecules of ammonia, ammonium phthalate, you are going to get carbon double bond oxygen, NH4 plus of minus, again double bond oxygen, O minus of NH4 plus of oxygen. This is ammonium phthalate, this upon heating minus 2 molecules of water, you get here, that is here. So here you are going to get CONH2, and here also you are going to get CONH2. So here, if you take, this is phthalamide, mind you, phthalamide, I am underlining. Again you have to heat this. If you are heating this, if you heat minus 1 molecule of ammonia is lost, and here you are going to get a new compound, that is benzene ring with the carbonyl group. Here also one more carbonyl group, and here you are going to get NH. This we are going to call it as phthalimide. Mind you, imide, it's an imide, IMIDE, phthalimide. This is phthalamide, this is amide, and this is imide, phthalimide. So that is the basic difference between phthalamide and phthalimide, and this is the sequence. So here reactions involving carboxylic acids. In this first one, we can take reactions involving carboxylic acid. The first one we can take, so reactions involving carboxylic acid, I repeat, reactions involving carboxylic acids. In this reduction reaction, reducing agent, you can take lithium aluminum hydride, or you can take diborane, lithium aluminum hydride or diborane. Then second is halogenation reaction. In this halogenation reaction, it's a named reaction, HVZ reaction. We call this as Hell-Wohlhard Zelensky reaction, and here the reducing agent is, it's like alpha substitution. This is alpha carbon substitution with the chlorine in the presence of red phosphorus. Third is decarboxylation reaction of carboxylates, salt of carboxylates. Here the decarboxylating agent here is, that is, we use NaOH plus calcium oxide in 3:1 ratio. We call this as soda lime. Decarboxylation reaction, and of course in the same decarboxylation reaction we can also subject it to Kolb's electrolysis. In the Kolb's electrolysis also we always get the product contains double number of carbon atoms in the product. So here there are four important reactions, that is reduction reaction. In the reduction reaction we are using reducing agent lithium aluminum hydride and diborane. Halogenation reaction, HVZ reaction, Hell-Volhard-Zelensky reaction, in which the alpha carbon substitution is taking place with chlorine in the presence of red phosphorus acting as a reducing agent. Decarboxylation reaction is done on the salts of carboxylates, and during the salts of carboxylates when we are using the decarboxylating agent as soda lime, the caustic soda and the quicklime, they are taken in 3:1 ratio, and that composition we call it as soda lime. And if you go for the last reaction, that is Kolb's electrolysis, in which the salts of carboxylic acids are subjected to electrolysis, and after the electrolysis is completed we get an alkane which contains double the number of carbon atoms of the salts of carboxylates which we have taken in the reactant side. So here let us go with the reduction reaction. Take the carboxylic acid CH3 single bond carbon double bond oxygen of OH. Take the lithium aluminum hydride, pass one nascent hydrogen. Take the lithium aluminum hydride as a reducing agent. So this lithium aluminum hydride converts the carboxylic acid is converted to the primary alcohol. So CH3 CH2 of OH. This is converted to primary alcohol. Similarly, if you go for halogenation, second reaction, go for halogenation. In the halogenation, take CH3 carbon double bond oxygen of OH plus take 3 molecules of chlorine in the presence of red phosphorus. This is alpha carbon. All the 3 hydrogens are replaced by the 3 chloro groups. Then you find the 3 chlorines being substituted by the 3 chloro groups are substituted by the 3 hydrogens. The 3 hydrogens are replaced and the carboxylic group remains as it is, and you get 3 molecules of HCl, and we call this as trichloroacetic acid. And this is acetic acid. This is acetic acid. This is HVZ reaction. This comes under the HVZ reaction. Then if you go for the next part of the reaction, that is decarboxylation, go for decarboxylation reaction. If you take simple reaction, it is CH3, salt of carboxylic acid, we are supposed to take O of Na, sodium acetate, in the presence of NaOH, taking calcium oxide as a catalyst, sodium acetate. Here you remove one molecule of sodium carbonate, the product is methane and the byproduct is Na2CO3. This is decarboxylation reaction. Then after decarboxylation reaction, go for Kolb's electrolysis. If you go for Kolb's electrolysis, take 2 molecules of sodium acetate, and you add here 2 molecules of water. Here also you add 2 molecules of water, subject it to electrolysis. You find that here the products obtained, here the bond breaks 4 times, 4 different products are obtained. So here you can take the product as one is CH3, single bond CH3 plus 2 molecules of carbon dioxide, and again 2 molecules of NaOH and 1 molecule of H2 gas. Because it's an electrolysis process, we have 2 electrodes. One is anode electrode and the other one is cathode electrode. Anode begins with A and cathode begins with C. So these two are gases. This is a gas, and this is also a gas. So these 2 products are obtained at anode electrode and these 2 products are obtained at cathode electrode. That is Kolb-base electrolysis for the preparation of alkane. So here you go for the last reaction, ring substitution. If you take in this, you can take first one, action of concentrated nitric acid plus concentrated H2SO4. This mixture we call it as nitration mixture. So HNO3 plus H2SO4 gives you NO2 plus nitronium ion plus 1 bisulfate ion plus 1 H2O molecule. So take the benzoic acid, COOH. Basically it's an electron withdrawing group, and it's a meta director. So therefore when you are adding this is electrophile. Take NO2 plus electrophile. So this is the meta position. So the electrophile is invited at the meta position. So you get here meta nitro benzoic acid. Next, similarly you can take, that is second one. If you take, so here if you take the second one, that is action of Br2 in the presence of FeBr3, catalytic halogenation. So therefore Br2 plus FeBr3 gives rise to 1 bromonium ion plus ferric FeBr4 minus. So this is the electrophile. And take this electrophile, continuation, take the benzoic acid and take the electrophile, bromonium ion is the electrophile, it is invited at the meta position. So here you are going to get the major product as metabromo. This is metabromo benzoic acid. This completes the carboxylic acid unit.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.